All right, everybody, we're coming back for the third section in chapter 4. This one's going to be on this relating the graphs of f prime, and f double prime. But before we get there, you might want to try to do this as a warm up to get you in the mood for everything. Notice we're trying to find critical points of the function. Probably your best bet for that one is to expand this polynomial so that we have x minus 2 times x squared minus 6x plus 9, and then actually multiplying it out so that we'll have, let's see, x cubed minus 6x squared plus 9x minus 2x squared plus 12x minus 18. So all said and done, all expanded, we'd have x cubed minus 8x squared plus 21x minus 18. Take the derivative of that, set equal to 0, solve, you'll be able to find your critical points. And then for number 2, you really do have to analyze that. So looking over Chahira, we actually have the answers. I would point out, I wouldn't use this table of values to analyze the second derivative. We do see that we have 2 critical points coming out of right here with that 3x minus 7 and the x minus 3. We should see that our 2 critical points are 7/3 and 3. So looking at that, if I was to analyze this nowadays, I wouldn't use that chart. I would use this f prime graph so that I can just have, let's see, my 2 critical points of 7/3 and 3. And then just plug in some random numbers to figure out that you got the positive, negative, and positive. Again, up, down, up. I'm looking for a maximum. 7/3 is my maximum here. All right, but let's get into, not that, this. Section 4.3, connecting f prime and f double prime with the graph of f. Way back of days, as my son would say, one of the important uses of derivatives was as an aid in curve sketching. Now we have it kind of easy in the curve sketching department, and the reason why we have it easy in the curve sketching department is because of our lazy bones machine. We have a graphing calculator that will do all of the work for us, although that's not really that cool. It's not really fun to use our calculator to analyze graphs. So we want to be able to do all the stuff that our calculator does it, but we want to do it and sound smart when we do it. So now looking over here, we've got some graphs here. You can actually see I'm trying to relate the f prime to the actual graph. So you can see starting over here at point A, we have an absolute minimum. We can only see that that is an absolute minimum if we look at the original function. We can find relative minima and maxima, but we cannot find absolute without analyzing the actual function. So looking from A, I can see from A to point C1, f prime is greater than 0. That means that the function is increasing on that point, on that interval. Now I see at C1, I do have an f prime of 0, so that would be a critical point. But if we were to analyze this graph using that number line that we had from yesterday, we can actually see from C1 to C2, we have still a positive first derivative, which means the function is still increasing and makes C1 not a relative extreme. We can actually see at C2, we have again f prime is equal to 0, but this time f prime changes from positive to negative. That's how we know that we have a local extreme value. The local extreme value happens to be a maximum because we go from f prime being positive to f prime being negative. Again, you can analyze all of this off of the Sine Chart that we use on that number line. From C2 to C3, we can again see that the first derivative is less than 0. That shows up as the function is decreasing. And then from C3 to C4, we can see that f prime is greater than 0, shows up as that function is increasing. Between, or at C3, we can see that f prime changes from negative to positive, which makes C3 a local minimum. Now at C4, we have f prime is undefined, again making it a critical point. Because the derivative changes from positive to negative at C4, that means that C4 is a local maximum. We can go back and look at the function to determine, since it is the highest over the entire domain, it is also an absolute maximum. Looking at C5, we have a critical point because f prime is equal to 0, but since the first derivative does not change signs at C5, C5 is not an extreme value. And then we look at B, the endpoint there, it is going to be a local min. All right. Let's move forward. First derivative test. That's all the stuff that I just ran through with you. We have if y prime is positive, the curve is rising. If y prime is negative, the curve is falling. If y prime changes signs, the point is either a minimum or a maximum. And if y prime does not change signs, the point is not a local extreme. And again, the thing that you want to use to illustrate this is the sine chart. Sine chart does not do the job of explaining stuff, but it can keep stuff organized for you. So we got A, C1, C2, C3, C4, C5, and B. We can use that sine chart in between each point. Again, I know f prime is greater than 0, positive. F prime greater than 0, positive. F prime less than 0, negative. F prime greater than 0, positive. Less than 0, negative, and negative. And again, I can find out where I have my local maxima and local minima just by looking at this sine chart. All right, now what we have hanging out up here is we have a graph showing us, trying to illustrate to us concavity, okay? So I'm sure you guys have heard concavity before. Way back in Algebra 2, you learned that you have something called concave up, where it's like that smiley face, and then you have something that's called concave down, which is like that frowny face. We now are going to have an opportunity to find out what those, how to determine where the concavity, where a function is concave up or concave down. Sorry, I couldn't figure out my words there. And what concavity comes down to is really the slope of a function. What you can actually see here, if I start way over, trying to grab that point and move it around, let me just use my mouse instead of my pen here. So you can actually see I can move this point A. And this point A, when I start all the way over to the left, it's very steep negative. And as I move to the right, that function kind of like starts to flatten out. It is increasing the positivity of its slope. It's gaining more and more positive slope. So as I move from left to right, when the slope is becoming more positive, we have this smiley face that's happening. When the slope becomes more and more negative, that's when we have this frowny face. So see how that slope is becoming more and more negative on that concave down situation? Now, since we're talking about our slopes, we know that we're talking about the derivative. There you can see we have the blue graph, which is our derivative graph. You can actually see where this derivative has a 0, we have a minimum. The other place where this derivative has a 0, we have a maximum, trying to illustrate that that connection for our critical points to our minimum and maximum. We can even see further when the function is increasing, or when the derivative is increasing rather, so we can see when the derivative slope is positive, we have this concave up. When the derivative slope is negative, we have this concave down feature. If I want to pull up the second derivative, and you can actually see over here I have the functions listed where I have the function is negative 2x cubed minus 7x squared minus 3x plus 2, the derivative being negative 6x squared minus 14x minus 3, and then the second derivative being negative 12x minus 14. That's showing up as red over here. Now you can see where the first derivative is increasing, the red derivative, or the second derivative, is above the x-axis. That's where we have the concave up. Where the second derivative is below the x-axis, that's where we have that concave down. So this is what we're talking about when we talk about the relationship between f prime, and f double prime. Let me get rid of this real quick. So that leads us into the definition of concavity according to calculus. The graph of a differentiable function y equals f of x is concave up on an open interval I if y prime is increasing on I. It is concave down on I if y prime is decreasing on I. That's great. How can I tell more about the function? So the second derivative, again, is the rate of increase or decrease of y prime. So if y double prime is positive, the curve is concave up. If y double prime is negative, the curve is concave down. If y double prime is 0, it's possible that's where the concavity changes, and that's what we call an inflection point. But we'll get back to that in a little bit, and this is called the concavity test. All right? I thought I was on the right. There we go. So let's use all that information to sketch a graph of y is equal to x cubed minus 3x squared plus 4. And just for ease of doing this, I've actually factored it already for you. And the only reason why I wanted to do that was this allows us to find two really easy points to graph. I happen to know what the what the y-intercepts are. No, not the y-intercept. The x-intercepts where y is equal to 0. I'm going to have x-intercepts wherever I have zeros of these. So the x-intercepts are going to be at x equals -1 and x equals 2. Only reason I want that is because ultimately I'm going to put this to a graph, and that just gives me two easy points to start graphing on here. So like, let's not do the graph yet. We'll get to that in just a minute. So again, two easy points. I got -1, 0 and 2, 0. We'll come back to those in a little bit. We are again going to use all of the information that we just learned. So we're going to use the first derivative test, the second derivative test, all to develop a good graph of this function. So for the first derivative test, I need to calculate the first derivative. So I go back up to y, I take the derivative, okay, not too difficult to find, 3x squared minus 6x, and 4 differentiates out. So now I want to find critical points. Critical points, so that I can find my maxima and my minimum. So critical points are going to be where the numerator equals 0 or the denominator equals 0. So here I can see my denominator of my fraction is 1, so 1's never going to equal 0, but I can set my numerator equal to 0, and I can even further factor stuff out. So I got 3x times the quantity of x minus 2 is equal to 0. I have my two critical points where 3x equals 0 or x minus 2 equals 0. So that means my two critical points are x equals 0 and x equals 2. Sweet. Awesome. That's great news. Now I'm going to look down here, and I'm going to use that to figure out where this function is increasing and decreasing. I'll even be able to figure out where I have my maximum and minimum values of this function. Again, I'm going to label this as y prime. I do that because I'm eventually going to put a y double prime graph somewhere, or number line somewhere up here. I want to keep them separate. So I'm going to put my critical points on here. 0 and 2. And again, all I need to do is find out the value, the positivity or negativity at these given, in between these given points, in the intervals. So looking here, if I'm talking about less than 0, I actually go up here to this factored form to figure that out. So if I'm less than 0, this is going to be negative. 3 times a negative, that term, negative. Over here, if I have a negative number, minus 2, negative minus is going to be negative as well. So I'm going to have negative times negative. This down here is going to yield positive. If that's too much for you, just plug in like -1. 3 times -1 is -3 times -1 minus 2. So it's -3 times -3. That gives me +9. I don't care about the magnitude. I just care about the sign. Between 0 and 2. Again, my mind goes to between 0 and 2, I have a positive. So this is going to be positive. And less than 2 minus 2, this is going to be negative. Positive times negative, I get negative. Doesn't work for you? Let's see. 1 is right in there. 3 times -1, yeah, negative. Looking a little bit further, bigger than 2. Well, bigger than 2 is positive, so this factor is positive. Bigger than 2 minus 2 gives me positive. Positive times positive means positive. Doesn't work for you? Use 10,000. 3 times 10,000 is 30,000. 30,000 times 9,998 is pretty darn positive, isn't it? So now I can actually see coming in from the left at 0, I have an increase. To the right of 0, I have a decrease. From the left of 2, I have a decrease. Right of 2, I have an increase. So it looks like I have a max at 0 and I have a min at 2. Well, at 0, my y value, I'm going to have 0, comma, looking up here, if I plug in 0, I've got, let's see, 0 minus 0 plus 4. That's 0, 4 is my maximum of my local max, I should say. It's not my absolute max, I don't know that for sure. And my min value here is going to be 2, comma, oh, I have to plug it in here. Actually, plugging it in here is going to be easier. Actually, 2 minus 6. Oh, I already knew that that was 2, comma, 0. All right, cool. So now I have a maximum value, I have a minimum value. All I need to do now is figure out my concavity of this function. And my concavity is going to come from my second derivative. So my second derivative, again, I've got my first derivative laid out right here. My second derivative is going to be 6x minus 6. To determine concavity, or the intervals of concavity, I want to find out where the concavity can possibly switch. So I'm going to do the same thing that I did down here, but I'm going to do it on the second derivative. So I've got 6x minus 6 equals 0. Solve that. I got 6x equals 6. I've got x equals 1. So my possible point of inflection is x equals 1. Looking at that a little bit further, I can do this same number line with my y double prime. Put my possible point of inflection at 1. And to the left of 1, I'm just going to try some test point, or maybe just figure it out conceptually here. So looking to the left of 1, 0. 0 minus 6, okay, that's pretty darn negative. To the right of 1, 2. 12 minus 6, okay, that's positive. So now I can see I have a concave down interval and I have a concave up interval. So now I'm just going to interpret all of this stuff into a list of words, and then I'm going to draw a graph here. So things that I can determine. I can determine where my function is increasing. Again, increasing versus decreasing is going to be on my first derivative. My first derivative, increasing, is wherever I see positive. So it's on this interval and this interval. My increasing interval is going to be from -infinity up to 0 and, let's see, 2 up to infinity. My decreasing interval, decreasing, is going to be wherever my first derivative is negative. So from 0 to 2. Further, I just figured out how I can determine where the function is concave up. So the function is going to be concave up where the second derivative is positive. Second derivative positive, that's from 1 up to infinity. 1 up to infinity. And concave down, wherever the second derivative is negative. That's over here. So from -infinity up until 1. All right, cool. Ooh, even further, I can figure out my maximum and my minimum. My local max, again, I don't know if it's an absolute max, is going to be at 0, 4. So we have a maximum value at x equals 0. I'm just abbreviating it by putting the point down. And my minimum is at 2, and it is 0. I will tell you that on your next test, this is a major question on your next test, being able to determine all of these things: intervals of increasing, intervals of decreasing, intervals of concave up, intervals of concave down, maximum, minimum, and even something that we haven't said yet, point of inflection. But if I look over here and try to draw my graph now, I happen to know that I've got two zeros at -1, 0 and at 2, 0. Even further, I happen to know that I have a maximum value at 0, 4, minimum value at 2, 0. Again, let's put that -1, 0 down. And again, I know that I change concavity at 1. 1, I can actually find out that I have a point of 1, and going over here, I can have 1 plus 1, 2, times 1 minus 1, 2, so -1 squared. So it would be at 1, looks like 2 here. So there's a point right there where I change concavity. Now what I'm going to look at here, I'm increasing from -infinity up to 0. So that means this is going to have to go up. Even further, I can tell from -infinity to 0, that falls into the concave down territory. So the concave down, I'm going to increase and look like a frowny face. Right there, I can see that I switch from increasing to decreasing at 0. So I'm going to make that frowny face come right down into here. At this point, I'm going to change my concavity from concave down to concave up. So all of a sudden, I'm going to turn to a smiley face. Until I get to this point right here, which is going to be my minimum, I'm going to hook back around. And what I've actually developed there is I've drawn a fairly accurate graph of the original function. Now, let's look at how accurate that graph is. Let's get that away from here so we can see the graph at the same time. And let me go into my y equals menu. There it is. I can type in x cubed minus 3x squared plus 4. Look at that. That's almost exactly what I drew on my paper without having to use my calculator. And it feels so much better when I do stuff without my calculator. So much better. All right. I said page down. There we go. There's all the work laid out pretty well for us. Now try this one out. Pause it, and then I'll come in and I'll do the work. So pause it. Well, before you pause it, you're just trying to determine where the function is increasing, where it's decreasing, where it's concave up, where it's concave down, maximum, minimum, and maybe a point of inflection. But we haven't officially talked about point of inflection yet. So pause. And now you can come back here. Again, when I do these problems, I like to start out just calculating y prime. I've got 2x plus 2. I might even throw in a y double prime at the same time just to ease myself up. I know that I'm eventually going to have to calculate both of them. I'm going to be doing the exact same thing with both of them. So the second derivative is just going to be 2. Now looking at this, I know for my critical points, I'm going to go back to my first derivative. I'm going to set my first derivative equal to 0. When I set that equal to 0, I'm going to get 2x equals -2. I'm going to get x equals -1. So my only critical point is -1. I go over here and I draw my y prime chart. I have my critical point, put that on the chart, and now I'm looking to the left of -1. Like if I plug in -2, 2 times -2, -4 plus 2 gives me a negative. Right of -1, 0. 0 plus 2 gives me positive. So now I can see that this function is increasing from -1 up to infinity, decreasing from -infinity up to -1. And again, all I'm doing is looking at the sign here. Further, I can actually see if I sketch this in here, down and then up, I can see that -1 represents the location of my minimum. If I find out what y of -1 is, y of -1, I can have -1 squared plus 2 times -1 minus 3. Let's see, 1 minus 2, -1, -4 is going to be my minimum. So I have a minimum value at -1, and the minimum value ends up being -4. Good so far? All right, cool. Now I have to go on to my second derivative. My second derivative, I have no possible, and again, I haven't used this term officially with you yet, but I have no points of inflection, so I'm just going to mark down the sign of my second derivative here. And the sign of my second derivative, well, 2. 2, is it positive or negative? It's positive. So that determines where my function is concave up, up, concave up wherever second derivative is positive, and that is from -infinity up to infinity, and concave down nowhere. Which means I have no points of inflection. Now if we look at what the graph of x squared plus 2x minus 3 is, it's a parabola. It's a happy parabola. We know that from algebra 2. So we know that it has that U shape. So we know that it's concave up everywhere to begin with, just from what we've known from all of math. But now we can actually prove it, which is a little bit cooler. All right, let's move forward. Okay, there's all the work. And now I'm going to officially say what a point of inflection is. A point where the graph of a function has a tangent line and where the concavity changes is a point of inflection. All right? So point of inflection. Point of inflection is where the concavity changes. It's not guaranteed that where y double prime is equal to 0 that you have a point of inflection, but it's possible. So you do have to test using that y double prime number line. We also have something called the second derivative test for local extrema. This one always got me. If you have a critical point where f prime of c is equal to 0, and if the second derivative is less than 0 at that point, then you have a local maximum at that point. If f prime is equal to 0 and f double prime is greater than 0, then f has a local minimum at that point. And this really, again, it's kind of counterintuitive to me, but if we look at number one, again, we have f prime is equal to 0, so it is a critical point. F prime is less than 0, that means that f double prime is negative and we have a concave down function. So the thing that I used to do whenever I would analyze this using the second derivative test, I would just draw, not even on a coordinate plane, I would just draw an example of a concave down. I might even draw it in the air. And I can see where f prime is equal to 0, okay, that's a maximum. So just drawing that picture really helps me out. And 2, if I have f prime is equal to 0, again, that's my critical point. If f double prime is greater than 0, that means f double prime is positive, and I have concave up, and I can see that minimum. Again, anytime I took a test where I had to do the second derivative test, you would see me going like this in the air, or like this in the air, and I'm sure I looked like an idiot, but hey, at least I was able to figure it out, right? So let's look here. Find any points of inflection and local extreme values of f of x is equal to x cubed minus 6x plus 5. So we see that we have points of inflection and local extreme values. Well, when I see points of inflection, that draws my mind to second derivative. When I see local extreme values, that draws my mind to first derivative. So the first thing I'm going to do is calculate f prime of x, and then f double prime of x. F prime of x being 3x squared minus 6. F double prime of x being 6x. The 6 differentiates out. Now again, I see that I have to have local extreme values, so I know that I'm going to have to find my critical points. My critical points are going to be where 3x squared is 3x squared minus 6. Forgot that minus 6. Where the first derivative is equal to 0. So I'm going to have 3x squared equals 6. I'm going to get x squared is equal to 2. I've got 2 critical points plus or minus square root of 2. Now I look down at my second derivative. I know that my possible points of inflection are going to be where my second derivative is equal to 0. So that's going to be where x equals 0. Now, I set all of these up without analyzing them because now I'm going to analyze them simultaneously. I'm going to put down 2 number lines. I'm going to put down an f prime and I'm going to put down an f double prime, and I'm going to analyze them at the same time. So now looking at these, I see on my f double prime, I'm just going to put a 0. I know I have 0 up here, but I'm not going to acknowledge it because it's not one of my critical points. But I do happen to know that I've got negative root 2, and I've got positive root 2. In order to find out if I have a maximum or a minimum at negative root 2 and positive root 2, I could do my first derivative test if I wanted to, but since I had to find my second derivative, isn't it easier just to figure out, like, to the left of 0, f double prime? Well, I'm plugging in negatives, so 6 times a negative, that's going to be a negative. And over here, I plug in numbers bigger than 0, so that's going to be positive. 6 times a positive gives me positive. I know I've got a concave down over here and concave up over here. That means negative root 2 is going to represent a local maximum. Positive root 2 is going to represent a local minimum. All I have to do, so now I can see. Local max at x equals root 2. Local min at x equals, local max at negative root 2. Local min at positive root 2. And of course, to find the y values, I would just have to plug these back into the function. So the local maximum would be f of negative root 2. The local min would be f of positive root 2. Woohoo! There we go. Alright. Oh, crap. It also said to find the point of inflection. Point of inflection is where the second derivative changes concavity. Where the second derivative changes sign, and we have a change in concavity. So I guess I did skip over this part. Point of not infection, inflection at x equals 0, where the second derivative changes sign. Here we have some summaries of how graphs can look. Remember, to be differentiable means a function has to be smooth, connected, graph can rise or fall. If y prime is greater than 0, that's something you need to know. Y prime greater than 0 means function increase. Y prime less than 0 means function decrease, so there's those two right there. Y double prime greater than 0, that means concave up. Here's how concave up can look. You've got concave up and increasing. You've got concave up and decreasing. You've got second derivative less than 0, concave down. So here's concave down and increasing, concave down and decreasing. Inflection point is where we change concavity, either from concave up to concave down or vice versa. If y prime changes sign, then you have a local max or a local min. If y prime equals 0 and y double prime less than 0 at a point, graph has a local max. If y prime equals 0 and y double prime greater than 0, we have a local min. All right, that is the entire section. So hey, that was hopefully painless. See you guys tomorrow.